Hello everyone. We are starting the next bunch of stuff that includes solid state components, and the first one we're going to learn about is capacitors. All right, pretty cool devices. Don't pay attention, you're going to get shocked on your butt. Okay, so I'm going to give you some info on it now, and then there's going to be some other videos that come up. I want you to watch them. They're going to involve a gentleman that changed a car battery into a capacitor battery and used it in his car. Okay, there'll be 3 videos. I want you to watch all 3 because he evolved from where he started to where he finished. Then you're going to have some other videos that are going to deal with the experiments in your stage 2 book. I am going to video me doing the experiment, and then you are going to answer all the questions in your workbook based off that video. Right? I believe there's 3 experiments this first time around, so we'll see how this goes. All right, so capacitors. You ever notice how you shut your TV off and a little light in the corner of the TV, the little LED glows and slowly goes off? Right? That's the capacitor in the TV that's keeping it that way. You ever been told don't open a TV, you're going to get killed? That's because there's capacitors in a TV, and they can hurt you very badly, all depending on how much energy is stored in them. Right? So let's look at a little history of these things. Right? Capacitor. Naturally, more than one capacitor is capacitors. Right? A device used to store electric charge consisting of one or more pairs of conductors separated by an insulator. When you look at a capacitor, if you were to cut it open, you'll see they're all, most of the time they're round, but you'll see this yodel of stuff inside, right? Just curled around and around. What that is a negative plate separated by a gap. That's called the dielectric. And on the other side is the positive plate. Power is going to flow through it, and stuff's going to happen with electrons. And you'll see what happens in a moment. So if you look over at this picture over here, right, you can see the negative charge attached to one set of the plates, the positive charge is to the other, the dielectric is in the middle, and you can see there's an insulator around the whole outside of it, right? You see that there's plastic on the outside, then you got an aluminum shell. These plates that are inside are metal with this gap in the middle. So these 2 guys, 2 different places, look at the dates, right? This guy was alive, Ewald over here was alive from 1715 to 1759, and Peter was 1692 to 1761. So you see that they overlap the same time frame. They were both alive at the same time. Around 1745, both of them figured out that there's a thing called capacitance in electrical circuit, right? 2 different studies. Both of them did it. Who gets the credit? They both did it. Same time. So really, they're the founders of this. They both discovered that electric charge could be stored for a period of time within something. And what they used was a Leyden jar. Okay? They sat down, they rigged this thing up, they stuck a chain suspended into this bottle. You had a metal rod. You saw this non-conductive top. That was a cork. You had a glass jar. Notice the insulation around the outside, an external metal coating, which took the glass, and the glass became the dielectric now. So you ended up with the negative charge on the outside. The inside was the positive plate. The glass was the gap in between, and what they did was, as you can see over here, they connected a power wire to the top. The bottom was grounded, and they looked at it, and they said, okay. Nothing happened. Right, let's take it apart. They touched a nail, they got zapped on their butt. They said, hey, there's a charge in that there bottle. Right then and there, they figured out that there was a charge stored inside, and they had to go investigate it further. Right? Amazing, 2 different people thought of doing this at the same time. Totally crazy. right? So this guy, John Bevis, in 1747, he lined the inside and the outside of the bottle with foil, and he made a capacitor with two conductors equally separated by glass. Okay, so they took this bottle, they lined the inside, they lined the outside, and they made the glass bottle as the insulator. Now you can see, here's where power would go in. This would be the ground side. These were your two plates. So obviously something happens on this side that makes it different than this side. In order for this to happen, we have to block these two plates from touching each other, and we get a dielectric sitting in the middle. Okay, so you're going to see that that dielectric in the middle, okay, is something that is a very poor conductor of electricity. Therefore, it becomes like almost like an insulator. Right, so if we look, we can see that vacuum, right, sucking all the air out of it, having an empty cavern there of stuff, has a dielectric constant of 1. Okay, that's its value. If we have air in there, it gets a little bit better, and now we're at 1.00059. If we fill it with polystyrene, right, like styrofoam, polystyrene, it now becomes a 2.5, which is better yet. If we put paper in there, and many times you find a paper in between those layers of the capacitor when you cut it open, paper alone, 3.5. Mica brings it to 5.4. Flint glass, whatever that exactly is 9.9. Methyl alcohol is 35, so a giant improvement. Glycerin, 56.2, and pure water is 81. All right, so you can see pure water, meaning water without any minerals in it, just water with everything filtered out of it, because anything that's in water is not, that's what carries the electrical charge within it. So we can see, naturally, if you go from vacuum to pure water, obviously the capacitor is getting better and better and better in quality. All right, so a capacitor consists of two conductive plates separated by an insulating material. That material is the dielectric. It's a poor conductor of electricity. The dielectric constant is the relative strength of the material against the flow of electrical current. The higher the number, the better the insulating properties. All right, so if you look at these modern capacitors, these are what you find in everything, absolutely everything. I want you to notice you got a measurement on there, right? You got a temperature range indicated on there. You have a negative stripe or an arrow, right? You see the little V there, right? This indicates the direction of current flow. So which way does current flow, right? From a positive plate to a less positive plate. Therefore, the current will come in, the power will come in on this side and come out the other side on the way back to ground. It's very important because you're going to see very shortly there's two different kinds of capacitors. There's polar ones and non-polar ones, right? Ones that have a polarity have a definitive positive and negative. If you hook them up backwards, boom, they pop. Smoke comes out of them and everything, and they're not good anymore. I had a student do that in the classroom, and that's why we don't put those in the boxes anymore when you get those test boards. All right, so the stripe indicates the direction of current flow, and if you look at these are three different pictures. You can see the same values on this one. Over here, you see other ones, and down here you can see that negative side with some temperatures on there. Right, so pay very close attention. Different capacitors are different strengths, and it's the difference between you going ow and you going thunk as you fall on the floor, not breathing anymore. So pay very close attention when you're handling these things.